Welcome to Chemistry 2, Unit 3, Lesson 2 on entropy. This is video 2. Last video, we looked at what entropy is, and we said it was a measure of molecular disorder. So the second and third laws of thermodynamics deal with entropy. The second law states that disorder in the universe is constantly increasing. So that means that if left alone, things tend to become messier. Think about almost anything. If you leave a car outside and you don't put any energy into maintaining that car, eventually it's going to fall apart. So we are constantly fighting this second law. If we don't keep up with anything, it tends to get messy and break apart. We spend billions and trillions of dollars each year trying to prevent this inevitable thing from happening. But if you do put energy into something, you can get it to be more ordered. But again, it costs energy. So that's the second law of thermodynamics. The third law deals with absolute zero. And that states that entropy at 0 Kelvin is 0. So what that means is at 0 Kelvin, there is no molecular motion present. So that means that there is theoretically absolutely no entropy or no disorder. Since this is a theoretical state, this basically means that as something gets colder and closer to absolute zero, the amount of entropy it contains is very low. So that can be seen in some of our effects that we're going to go over. So we're going to look at how entropy changes can be described on more of a qualitative front right here. So the first thing that we're going to look at is temperature. How does temperature relate to entropy? So again, because of that molecular motion, we know that if we add heat, things move quickly, our molecules move more, that is going to increase the tendency for things to be less structured. So if we have an increase in temperature, that will increase entropy. Now, it might not increase it all that much, but it does. And vice versa. If we decrease temperature, we have a decrease in entropy. That relates to the next one, which is state of matter. So we know if we increase the entropy, we speed up the molecules, they break the intermolecular forces, and they become more random. So as we go from a solid, which is fairly ordered, to a liquid, we don't have that structure anymore, so we have an increase in entropy. So if we look at solid to liquid to gas, we know that we can change those, but if we go in this direction, we are increasing entropy. So we end up with a positive delta S. So if we go from a solid to a liquid, we're increasing the disorder. Liquid to gas, we're increasing the disorder. And the opposite is true. If we go from a gas to a liquid, we are decreasing disorder. So it's a negative delta S. We're decreasing entropy. Letter C is dissolving. And hopefully this one is self-explanatory to you. If you go from a solid to an aqueous state, we increase entropy. That hopefully makes sense because when you are dissolving something like salt, you're actually breaking the NaCl structure into ions, and you have Na plus and Cl minus floating around in a random motion within the water. There are some interactions, but you are increasing entropy. And the last one deals with moles. So I'm going to use a balanced chemical equation. NH3 gas plus HCl gas yields NH4Cl solid. So if we have these gases going to a solid, that kind of gives you a little clue about state of matter and entropy. But we also look at how many moles we have on each side of the equation. Over on this side, we have 2 moles, and on this side, we have 1 mole. So if we're taking 2 moles of something and putting it into 1, we are decreasing the entropy. If we looked at this in the reverse, it would be increasing entropy because we're taking one thing and we're getting 2 from it. So we're destroying some of that structure. This is a pretty neat demonstration, but these 2 gases are not very great to release in a room. But if I were to have a container of NH3 gas and a container of HCl gas, and I were to release them at opposite ends of the room, somewhere in between where the 2 gases meet, you would see like a fog because you have solid ammonium chloride forming. So it's getting very, very structured when these 2 things react together. So we have a huge decrease in entropy with this reaction. So we can look at moles. If we have the same number of moles on each side, we can't really determine what's going to happen with entropy. So we might have to use states of matter. Here we have 2 gases going to a solid, which is really a big decrease in entropy, gases to a solid, but we also have 2 moles going to 1, so that both of those together reinforce it. If it was, these were all solids and we had a solid, we couldn't use that. So sometimes things are a little bit hard to tell, and as long as you explain it, it's fine.